Hello. In this video we're going to go through this one-pager, and it is on bases. These one-pagers are designed for students taking DP Computer Science, and they address a very targeted skill that they need to be able to do in a brief manner. But this is good for a lot of students who are studying computer science in general. So what we want to talk about is the different ways to represent numerical value. We count in base 10, and that's because we have 10 digits that represent value. That's 0 through 9. You can count in any base. It turns out that base 2 and base 16 are particularly useful for programmers. Base 2 is called binary, and it uses the digits 0 and 1. So in the same way that we have base 10, and we can go 0 through 9, and then when we run out of digits, we make a new units holder. In base 2, you only have 2 digits in that world. You have 0 and 1. Base 16 is called hexadecimal. And so base 16 has 0 through 9, but actually you can continue to represent those numerical values with using one character. And what they do is they use letters to do that. So in base 16, A means 10, B means 11, C means 12, D means 13, E means 14, and F means 15. So you kind of have to train yourself that when you see a B, you know that's 11. And we can see this nicely on this table here. And I'm just going to zoom out a little bit so you can see the whole table. There it goes. So if I asked you to fill in this base 10 table, we can do that pretty easily. We start here with the ones unit, and we say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And now we've run out of digits to use, so we write 10. So we say 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. And that should make sense. Now, if we're working in base 2, it turns out we can quickly write out the base 2 values in a table using that trick we looked at in our first one-pager. So remember when I talked about setting up a table of ones and zeros, a truth table, which is a table that represents all possibilities, is we can do this very quickly by following this pattern. In the first column, we put 0, 1, 0, 1, 0, 1 all the way down. And in the second column, we put 2 zeros, 2 ones, 2 zeros, 2 ones. In the third column, we put 4 zeros, 4 ones, 4 zeros, 4 ones. And in the last column, we put 8 zeros, 8 ones. So what we're doing is we're increasing the frequency that we repeat by a power of 2 each time. So this is 1, 2, 4, 8. And by doing it this way, you can very quickly map out all possible inputs. And by following this sequence, they now line up really perfectly, because 0, 0 in base 10 is the same as 0, 0, 0, 0 in base 2. And we would just write the straight 0 in base 2, but we're going to write 4 zeros, and you'll see why in a second. 0, 1 is 0, 0, 0, 1 in base 2. 2 in base 10 is 0, 0, 1, 0 in base 2. And we can follow this all the way down the table. And we see that, for example, 15 is 1, 1, 1, 1. And we'll talk about how we calculate this in a minute. At the same time, we can write base 16 over here. So remember, base 16 has 16 different symbols to represent numerical value. They have 0 through 9. So whether you're counting in base 10 or base 16, if you see a 9, 9 means the same thing. But when we get to 10, we write an A. So A in base 16 is 10. B in base 16 is 11. C in base 16 is 12, and so on. And we go all the way to F. And this is a really standard table that all computer science students want to be comfortable understanding and reproducing. This is why we have 4 digits in base 2, because F is 1, 1, 1, 1. And by writing this table, we account for all possibilities in our hexadecimal. So a quick skill that we want to kind of develop here, and we can zoom in a bit, is we want to be able to convert from base 2 to base 10. And there's a bunch of ways you can do this. And so one way that I like to do this is I like to do the following. Is I take a look here, and this is the number that I want to convert from base 2 into base 10. We know that this is a binary value because there's a sub 2 there. This is a little thing that's really important. There's a little subscript that indicates the base that we're counting in. Now when we're counting in base 10, we don't write the subscript because everyone just assumes we're in base 10. But technically, if that little subscript 2 wasn't there, that could equally be a base 10 number. And it should be interpreted that way. It actually requires that 2 there to say this is a binary number. So how do we do that? So one way to quickly do this is we write down the powers of 2 in sequence. So 1, 2, 4, 8, 16, 32, 64, 128. And each of these positions are contributing a power of 2. So this is the unit digit, the 2's digits, the 4 digits, the 8 digits, the 16th digits, the 32's digits, the 64 digits, and the 124 digit. In the same way that when we think of base 10, if I have something like 342, we learn to write this as 3 times 100 plus 4 times 10 plus 2 times 1, right? 3 is in our hundredths unit, 4 is in our tens unit, and 2 is in our ones unit. Binary works the same way, but instead of using powers of 10, we use powers of 2. So now when I take this number and I write it down, so I go in 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 0, 1, I see which ones are turned on. So this in base 10 is 128 plus 16 plus 4 plus 2. And that is how we can very quickly convert binary into base 10. So we know that 10010110 is 150 in base 10. And here's a little bit of deeper reasoning for you. Like I said, if we take 562, that's like 5 times 100 plus 6 times 10 plus 2 times 1. And we can rewrite that using powers of 2. So 562 is 5 times 10 to the squared plus 6 times 10 to the 1 plus 2 times 10 to the 0. So notice we're increasing by a power of 10 each time. So we take our binary number and we do the same thing. So if I have this number, which is right here, there's that number I've used down below. Notice I've written it here. It's 1, 0, 0, 1. Maybe I'll change let me pause and change the color of these. So I've put the binary value in here in orange. So I just start on the right hand side, and that's 2 to the 0. So 0 times 2 to the 0 plus 1 times 2 to the 1 plus 1 times 2 to the 2 plus 0 times 2 to the 3 plus 1 times 2 to the 4, 0 to the 5, 0 times 2 to the 6 plus 1 times 2 to the 7. And then I just do my calculations. And that's it. And like I say, here's the thing. This works for any base when converting to base 10. If the base was 3, you'd use powers of 3. If the base was 5, you'd use powers of 5. We happen to use base 2, base 16, and actually base 8 as well, is because they work really well with computers. Computers only work in base 2 because it's on or off. But base 16 is really nice because it's a power of 2 and it allows us to simplify representation. So here's another quick skill that we want to be able to do is we want to be able to convert base 10 to base 2. And so what I like to do when I do this is we write down the powers of 2 vertically starting from 20. Starting from 20 and stop when you hit a value larger. Sorry, that should be starting with 2 to the power of 0. Starting from 1, and stop when you hit a value larger than the number you're converting. So my number is 562, and I'm going to say 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. 1024 is bigger than 562, so I'm going to stop. And now the next step is you're going to find the largest value that fits. So we can add 512, that's less. So working from the bottom of the table, identify the largest value that is less than 562 and place a 1. There's my 1. So then I'm going to take 562 and subtract 512, and that gives me 50. And now I'm going to look up the table. So note this is bigger than 50, bigger than 50, bigger than 50. This 32 is less than 50, so I'm going to turn that one on. And 50 minus 32 is 18. And I go up. 16 is less than 18, so I'm going to turn that one on. So 18 minus 16 is 2. So bigger than 2, bigger than 2. That's the same as 2, so I'm going to turn that one on. And then 2 minus 2 is 0. And when we reach 0, we're done. So now we fill in the rest of the table with zeros. And now we can write this representation. So starting from let's zoom out a bit so you can see it all here. So we start from the bottom and work our way up. So we have 100110010. So that in base 2 is the same as 562 in base 10. So this takes practice. And this was a really quick explanation. Again, this is a one-pager where I've done some lessons with my class and talked about it. And how do you practice more? You can do this binary. You can do this binary to base 10 or base 10 to binary. So go to the link, pick a number, convert it manually, enter the number of the link, and confirm you're correct. That's the best way to do it. Alternately, you could actually write a program to do the conversion, because by writing a program, it's really going to drive in that understanding. So with that said, I hope this video helped. If you have any questions, please don't hesitate to reach out. And I'm going to include a shared link to this actual one-pager on here if you want to actually access it. Have a great day.